So we briefly talked about the field theory version of Fermi theory of beta decay, where the interaction Hamiltonian was written in analogy to QED. So you first write the four fields of the four fermions involved in the process, and you put a coupling constant in front, and I discussed in the last class that one can view it in terms of a massive particle being exchanged between proton and neutron on one side and electron and neutrino on the other side. By the way, we also wrote the corresponding term for QED, but I have not seen this discussion anywhere, but I personally think this is a very important step that Fermi took, because here is one case where one had to use quantum field theory. The various processes in QED, for example, the Compton scattering, the scattering of an electron with a high energy photon, or what is called molar scattering, scattering of two high energy electrons, most famously Gaba scattering, an electron positron annihilating each other, but then an electron positron being created. And there is also another process which is called pair production. Or which one can write in this form. I have a high energy gamma ray, and this you should work out for yourself, that a high energy gamma ray cannot go into an electron positron pair, because you cannot simultaneously satisfy energy conservation and momentum conservation. However, when the high energy gamma ray passes close to a nucleus, then nothing much happens to the nucleus, but under the Coulomb field of the nucleus, it can then pair produce. Then you can satisfy energy and momentum together. So, in all these processes, are actually two other famous processes are the following: E plus E minus going into two photons. All these processes, people actually have done calculations using field theory, but you can also do these calculations using only Dirac equation without explicitly using field theory. In field theory, you are talking about a creation operator and an annihilation operator. Whereas in quantum mechanics, you have this concept of conservation of probability. So if there is an electron, that electron is there all throughout. Nothing happens to that electron. So using Dirac equation, but using the quantum mechanical ideas, one can actually do all these calculations. But in the case of beta decay, I am compelled to use field theory. I mean, where is this electron coming from? I have to create it at the instant when the neutron is decaying. So, in that sense, in my opinion, this Fermi theory of beta decay is the first non-trivial application of quantum field theory. But it became obvious quite soon that there is a serious problem with Fermi theory. The actual beta decays is not quite this, but it is nucleus 1 going to nucleus 2, and this nucleus 1, I hope you have learnt about this in some nuclear physics course that you have studied. Typically, a nucleus carries some angular momentum. Nucleus 1 in general carries some angular momentum J1, and similarly, nucleus 2 also carries an angular momentum, some J2. And if you look at all the beta decays that were observed and looked at the values of J1 and J2, you find that there are cases where J2 is J1 plus 1. There are cases where J2 is equal to J1, and there are cases where J2 is equal to J1 minus 1. So, the statement made is that you can have delta J equal to 0. Delta J, of course, is but it is quite easy to see that Fermi theory, or what we call Fermi Hamiltonian, describes why is that? To see that, let us see this part of the Fermi Hamiltonian, and these fields, both proton and neutron, are fermions, and the fields, there are two parts to it. There is the creation and annihilation operator, and there is an associated spinor. So if I look at the spinor aspect of it, it looks like this. The creation and annihilation operators, they act on the external particles and take care of that. leaving behind this spinor part. And here you should remember how the Dirac spinors are written. Note, neutron is at rest and proton moves, but it is non-relativistic. So for a particle at rest, we write the Dirac spinor like this, where this is a two-component spinor and the bottom two components are 0. And for a non-relativistic particle, the force spinor looks very similar. Okay, the bottom two components will not be 0, but they are so small, they go like P by E. And for non-relativistic particle, P by E is quite small. So I have chi P dagger 0, gamma alpha. And if I look at the structure of these gamma matrices, gamma 0 is diagonal, identity minus identity, but gamma I are off diagonal. So, or let me not put 0 here, let me put P by P. So the gamma I couples this small P by E to chi n. So it's that corresponding amplitude is quite small. The dominant amplitude comes from gamma 0, which means that this looks like chi P dagger chi n. It means, and this will be 1 if both proton and neutron are spin up or both of them are spin down. If one is spin up and the other is spin down, this is 0. But if both have the same spin, then spin of the nucleus is not changing. So this will be is non-zero only if delta J is 0. So there seems to be a problem. I see nuclear beta decays with delta J plus minus 1, but I cannot describe them using Fermi theory. So people said the interaction, it has two parts. One we call the Fermi and one is called Gamow-Teller. And Fermi is what I wrote, product of this times the corresponding electron neutrino current. And the Gamow-Teller part, we call it G Gamow-Teller, psi bar P, gamma alpha, gamma phi, psi n, psi bar E, gamma alpha, gamma phi, gamma u. So as far as the fermion fields are concerned, it looks exactly same as the Fermi theory. Only difference is, instead of gamma alpha here, I put a gamma alpha, gamma phi, and here also I put a gamma alpha, gamma phi. By the way, this is called a vector current and this is called axial vector current. Now you can see, because of this gamma phi, so gamma 0 is 0 identity and gamma 5 is so because of minus sign here. So because of this gamma 5, now gamma 0, gamma 5 is off diagonal, and gamma I, gamma 5 is diagonal, and because of which you find that what I get now. So it is the gamma I, gamma 5 which will now contribute, and you will find that I have chi p dagger sigma I chi n. Now, sigma I, there are three things. Sigma z is diagonal, but that will not contribute because I write chi p dagger 1 0 0 minus 1 chi n. It looks as if this is giving, so this will give 1 for chi p chi n spin up and minus 1 for chi p chi n spin down. So if both are 1 0, I get 1, both are 0 1, I get minus 1. But I am not measuring the spins, so I have to sum over the initial states, and when I sum over I will get 0. But for 1 and 2, I get the non-zero matrix element when chi n is 1 0 and chi p is 0 1, or chi n is 0 1 and chi p is 1 0. So these matrix elements are non-zero when chi p chi n are opposite, that is when delta j is equal to plus minus 1. A priori, this is a completely independent Hamiltonian, and the coupling strength in front, it need not have any connection to the interaction that Fermi wrote down. So you take a delta j equal to 0 transition, make a measurement, compare it with Fermi Hamiltonian, determine G. You take a delta j equal to plus 1 or minus 1 transition, make a measurement, compare it with this, and you determine the Gamow-Teller coupling, and they come out to be the same. So we will not put any subscript. We call this also G. So we say that the interaction Hamiltonian is G times a vector times vector current plus axial vector times axial vector. Now, this is the start of a hint, but people were really taken up by this hint. It's what is called universal Fermi interaction. A priori, there is no reason for the coupling of the Fermi Hamiltonian and the coupling of Gamow-Teller Hamiltonian to be the same, but they are. So people began to suspect that weak interaction also is a universal interaction, just like the electromagnetic interaction is a universal interaction. Like the electromagnetic interaction in atomic physics, atomic electromagnetic interaction in nuclear physics, electromagnetic interaction in particle physics, or for that matter, electromagnetic interaction in the production and detection of electromagnetic radiation. It's all described by one single interaction. Similarly, people started, this gave the first hint that maybe there is a universal weak interaction. And it turned out to be a very powerful idea because there are a lot of cases where new aspects of weak interactions were turned up in experiments. But people held on to this idea of universal weak interaction, so they were able to modify the theory so that the modified theory incorporated the universal weak interaction idea, but could explain both old data and new data. Let me give one example. I hope you've heard of this symmetry called parity, which is you change the right-handed coordinate system into a left-handed coordinate system, and some vectors change sign under parity and some vectors don't change sign under parity. For example, position vector, momentum vector, they change sign under parity, but angular momentum, which is r cross p, does not change sign under parity. So this vector current is like that vector. It changes, the time component doesn't change, but the spatial components change under parity. Whereas axial vector current, time component changes sign under parity, but spatial components don't. So in that sense, relative to V, A has an overall minus sign under parity. And both Fermi and Gamow-Teller wrote their interactions as V dot V and A dot A because they sort of purely, you can say inertia if you want, but they believe all interactions conserve parity. All interactions are invariant under parity. That is why Fermi wrote V dot A, V, and Gamow-Teller wrote A dot A. But later, it was found that weak interactions do not conserve parity. So, question is how to incorporate parity violation in the beta decay Hamiltonian. There were various, the whole thing took place over 2 years between 1955 to 1957 or 58. But finally, Sudarshan and Marshak and also Feynman and Gell-Mann suggested that the interaction is actually V minus A times V minus A. So the constant in front I'll come to a little bit later, but let us look at this structure. Okay, let me put G by root 2. and why the root 2 we'll see in a minute. So if I expand it out, I get g by root 2 times v dot v minus v dot a plus a dot a minus a dot b. Now, okay, this looks like the Fermi, this looks like gamma Teller, but here there is a g, but here there is a g by root 2. And now you see that this v dot v under parity does not change, but v and a have opposite transformations under parity, so this will change sign under parity. Similarly, a dot a does not change sign, but this will change sign under parity. So this interference between vector and axial vector, those terms, they are parity violating. Now, why did I put? Question is, this v dot a term, I know that the first thing has to be v for delta j equal to 0, and the first thing has to be a for delta j equal to plus minus 1. That is what I discussed so far. But is this term contributing to the delta j equal to 0 transitions? Answer is yes, and if you work it out, you will find that the matrix element square is g squared by 2 times v dot v mod square plus v dot a mod square minus twice the real part of v dot a star, v dot v. As far as delta j equal to 0 transitions are concerned, for delta j equal to 0, these a terms don't contribute. Only these v terms will contribute. And so I have sort of a minus b. So if I take the square, I have a square plus b square minus 2ab. Now, when I put in all the kinematical details and integrate over all the final state momenta, because typically in beta decay we are only measuring the energy of the electron, we are not measuring anything, we are not measuring any directions. So if I integrate over all angles, you will find that this term will give 0. So this term is not contributing to the total decay rate. And this term are contributing equally. So you see, that's why I have made this g squared by 2. Whereas in the case of here, I have g square v dot v whole square. And when I integrate it over all angles, I get something. And you can verify that if I take v dot a whole square, integrate over all angles, the contribution is exactly same as v dot v whole square. And Fermi constant is a well measured constant. So instead of redefining the coefficient here, what people did is retain that symbol g and put a 1 over root 2 so that you get a match. And exactly same argument applies for delta j equal to plus minus 1 also. Mod square of this is same as mod square of this, and the interference term vanishes when you integrate over all angles. So you get a match with the Gamow-Teller Hamiltonian also. So and now actually you say the interaction Hamiltonian has a much neater form compared to here. Here you have sum of two products, but here you have a single product. And having said that, people also made the next step. Given a fermion, I can take what are called two chiral projections. One we call psi L, and other we call psi R. And we account for the fact that weak interaction has this form by saying that only left chiral fermions have weak interactions and right chiral fermions don't. Why should that be? We have an answer for that also. I hope all of you have done full-fledged course on quantum mechanics, and I hope whoever taught you quantum mechanics hammered you enough about something called irreducible representations of angular momentum. That construction of the angular momentum matrices j equal to half, j equal to 1, j equal to 3 halves, and also addition of angular momentum and all that. Why do we bother so much about the angular momentum problem in quantum mechanics? The reason is an interaction Hamiltonian has to be rotationally invariant. So when I take matrix elements of that Hamiltonian between some initial state with angular momentum J1, projection of angular momentum M1 to a final state with angular momentum J2 and M2, I can easily find out in which cases the angular moment, the transition matrix element is 0 and non-zero. Because the conservation of angular momentum actually makes a large number of these matrix elements 0. So this business of conservation of angular momentum is most straightforward to implement if I use these irreducible representations of angular momentum. We extend the same concept to relativity. In the case of rotations, I have a symmetry group which goes under the name SO3. Whereas in relativity, I have another symmetry group which goes under the name SO3, 1. Now, I find irreducible representations of this symmetry group, SO3, 1. And when I do that, I find that as far as spinor representations are concerned, the irreducible representations, they are not the Dirac fermion psi, but instead they are the Dirac fermion, they are these projections psi L and psi R. And if I want to build a relativistically invariant Lagrangian, I should start with these irreducible representations and put them together according to some standard rules so that I can construct a relativistically invariant Lagrangian. So my basic building blocks are these chiral fermions, and a priori the quantum numbers associated with those chiral fermions under some other interactions, they can be anything. So the question actually is, why is the electric charge of psi L and psi R electric charges of question shouldn't be why is parity violated, why are the weak interactions of psi L and psi R different. Question actually should be, why are the electromagnetic interactions of psi L and psi R the same? As far as I know, there is no answer to this question, except that we want parity conservation of electromagnetic interactions. So that's why we impose same charge on these. But there is no better answer than that. By the way, there are two further developments regarding weak interaction Hamiltonian. I hope you have heard of something called strange particles. And it was found that strange particle decays seem very similar to beta decay, but when you measure the strength of that weak interaction, which is causing the strange particle decay, that's a factor some 5 or so different from Fermi constant. So that was a puzzle, and that was resolved by Cabibbo using a concept called fermion mixing. So the concept of universal Fermi interaction is restored. Then soon after, another phenomenon, very important phenomenon called CP violation was observed, which was a big puzzle for about 10 years until two Japanese physicists called Kobayashi and Masukawa. They constructed a theory of weak interactions, again utilizing the principle that all particles should have the same weak interaction, which could explain CP violation. But in doing so, they said that there should actually be 6 quarks, only 3 quarks were known at that time. But later experiments showed that there were indeed 6 quarks. So there are at least 4 steps. This delta J, there is the Gamow-Taylor correction, then construction of V minus A theory, construction of Cabibbo theory, construction of Kobayashi-Masukawa model. In 4 different cases, the theory was developed based on this idea of universal weak interaction. So Fermi proposed the theory, and then Gamow-Taylor added their correction, and people compared the predictions of this theory with experiment. There was a very nice match. So which sort of convinced people that yes, there is a third particle involved in beta decay. But the question is, how to detect this third particle. And in fact, Pauli, who made the original proposal, he seemed well aware that it would be sort of practically impossible to detect this third particle. And supposedly in some place he actually made this comment that, oh, I did something very terrible. I predicted the existence of a particle which cannot be detected. And in fact, I'm trying to remember the names. I think it is Hans Bethe and Otto Frisch who did this calculation. So you have beta decay, you write as and you take electron to this side. So then we have but in chemical reactions, for example, you write A plus B equal to C plus D, but you also say that if I sort of change the environment, change the pressure, temperature, etc., in principle, the inverse reaction is also possible. So this is the situation that somebody considered. So I have a proton sitting at rest and I hit it with a neutrino, and a neutrino of a high enough energy, let us say neutrino with energy of 5 MeV. Then proton energy is 938 MeV. This neutrino has energy 5 MeV, so 543. Neutron mass is 539, electron is 0.5, 539.5, so energy conservation allows it. And of course there are two particles here, so I can always adjust the momenta so that momentum conservation allows it. So if I take a antineutrino of high enough energy of around 5 MeV or so, then this reaction should be possible. So just as an intellectual exercise, I think this is Frisch and Bethe calculated you have the Fermi Hamiltonian, and the same Fermi Hamiltonian is responsible for beta decay and also for this reaction. So use the Fermi Hamiltonian and calculate the rate for this decay. And obviously this is proportional to G square. G square times what? Well, in some sense it should also be proportional to sort of the Q value here. We have to take that into account, but we can do some kind of we can do some kind of dimensional analysis. So sigma has dimensions centimeter square, which means that it has dimensions energy power minus 2. And G square has dimensions energy power minus 4, so I have to multiply it with with dimensions energy power 2. And that quantity should be Lorentz invariant if I make a Lorentz transformation anywhere in this direction, because the cross section, if I go from this so-called lab frame to center of mass frame, the cross section shouldn't change. If it is differential cross section d sigma d omega, that will change because that omega depends on the frame. Or d sigma dE, that can change, but the cross section is perpendicular to the direction I am making the transformation. So I should construct a variable with dimension energy square, which is Lorentz invariant if I go from lab frame to center of mass frame. And one should, in this problem, this actually is slightly non-trivial problem, but one can construct such a variable. And then you substitute the value for g square, and you will find, let's actually do this, g square mp power 4 times something by mp square. So this g square mp power 4 is 10 power minus 10, and sorry, I made a mistake here. So something by mp square times mp square. Yeah. This is of order, this has dimensions energy, so I write that quantity by mp whole square times 1 over mp square. So this something times mp square, and I convert this into centimeter square. So this is what we use. H cross C is 0.2 GeV Fermi. So 0.2, and MP is 1, I say. Fermi square. And Fermi is 10 power minus 15 meters. So this is 0.04 into 10 power minus 30. Sorry, minus 30 from here, minus 40 from here. So minus 40 times this quantity by mp whole square meter square, or I will write it as sorry, 4 times 10 power minus 42 meter square. But let me, this quantity here, I have to do a more exact calculation, but just to get a feel for the number, let me put 5 MeV, or let me put 10 MeV. I'll assume that my neutrino energy is 10 MeV. I'll just put that. So that is 0.01 GeV. So I get a factor of 10 power minus 4 from here. So I'm getting 4 into 10 power minus 46 meters. The actual answer will be some within a factor of 10 or so of this. But this is my guess for the cross section for this process. And I hope you are familiar with this unit called barn. So in terms of barns, this is about 10 power minus 22 barns. And the cross sections that were measured in the lab, let's say for Compton scattering or molar scattering or Baba scattering, they are of the order of barns, maybe millibarns. But this is some 18 to 20 orders of magnitude smaller. So people were convinced that a neutrino cannot be detected. And in fact, the same beta, whose name I mentioned, around the same time has written a famous paper about production of energy in stars due to nuclear fusion. And in writing those fusion equations, he omits writing the neutrino in those equations because according to him, it is there to take care of energy momentum conservation, but it's not really visible, so one need not bother about it. But, well, depending on your point of view, fortunately or unfortunately, World War II happened, and during World War II, nuclear reactors were constructed, and then nuclear bombs were constructed. And once the war was over, people started thinking of possible uses of nuclear bombs other than to kill one another. And in fact, the name Teller I mentioned, he wanted to use nuclear bombs to build canals. Okay. Building a canal means you have to dig a lot. He said, instead of digging, let's just put a bomb and blast things out. And somebody else came up with this brilliant idea. Nuclear bomb consists of macroscopic amounts of nuclear material. So you are talking about an Avogadro number. Okay. If not Avogadro, milli-Avogadro number of atoms. And they are all undergoing nuclear transformations within a second. So you get a blast of 10 power 20 neutrinos. And okay, you have a cross section which is 10 power minus 22 barns. But if you build a good enough detector which can stand the blast, you can see the neutrino interaction. That was the proposal made. Apparently, it was considered quite seriously until first people decided it's difficult to build an equipment which can stand the nuclear blast. And number two, even if the equipment can stand it, the scientists can't. Anyway, the final proposal was, instead of getting 10 power 20 neutrinos in 1 second, you look for 10 power 13 seconds over 10 power 7 seconds. The net product is the same. So that was the proposal finally accepted. So, at a nuclear reactor, two experiments were launched to detect these neutrinos that are emitted by the beta decays taking place in a nuclear reactor. And of course, people were aware of thus what is possible, what are called backgrounds, that is interactions which have nothing to do with neutrino interaction but which will mimic the neutrino interaction signal. And here actually this is a nice proposal because the nuclear reactor is periodically shut down for maintenance, and if you continue to take the data, then you are measuring the background separately, and of course when the reactor is on, you are measuring signal plus background together, and you can make a distinction between the two. So you want nu bar interacting with the proton. Suppose this interaction takes place. First, how do I identify this interaction? Quite often in these interactions, we detect only one of the final state particles. But positrons were discovered in cosmic ray interactions already. So detecting only positron is not good enough. One has to detect positron and neutron both. And also you need proof so that the positron and neutron are both produced in the same interaction. It's not like I detect the positron now and I detect neutron 5 minutes later. So how to do that? What happens when a positron is produced in a detector? Any guesses? Yeah. In the detector, there are Avogadro number of electrons, so it's trivial matter for the positron to find an electron, annihilate, produce 2 photons. So in that sense, production of these 2 flashes of light, it's a hint that maybe a neutrino interaction has taken place. Next is, how do you detect the neutron? Neutron being a neutral particle, its detection is more difficult. And also, this is a fairly high energy particle with energy between 5 to 10 MeV. So when such a particle hits the proton, it gives the produced neutron has some non-trivial amount of kinetic energy. It's not very large, but thermal kinetic energy is milli-electron volts. But this neutron may have kinetic energy of order of electron volts. So the neutron is non-relativistic, but V by C is probably, I don't know, 1 part in 1,000, which is a large speed. And you need to slow it down before you can detect it. That is point number 1. And point number 2, of course, you actually need to detect it. But the first part of the problem was already solved when people built the nuclear reactors, because in a nuclear fission, those neutrons actually have, again, quite large kinetic energies. By large, I mean of the order of tens of electron volts maybe. And in order for such a neutron to create the next fission, you need to slow it down. And so this business of moderators were developed. So that part of the problem was solved. So you put moderators in your detector. And second thing, to detect the neutron, people put cadmium rods, and cadmium rods actually act as moderators also. And the neutron gets absorbed by the cadmium, goes into an isotope of cadmium, which is highly unstable, but it decays into a same isotope but of lower energy by emitting a 2.2 MeV gamma ray. And so the produced neutron, it has non-trivial amount of kinetic energy, and it takes some time for that neutron to sort of have collisions with the moderator, lose its energy, and be captured by cadmium. Of course, this is a random process, so the time for it is not fixed, but one can, even random processes have a time scale, and it is estimated that the time scale of this process is a few microseconds. So the signal that was identified is the following. Two gamma rays with total energy with first each with E gamma greater than 0.5 MeV. Mind you, the positron can have a few MeV kinetic energy. So when it annihilates with an electron, the total gamma rays together will have some 4-5 MeV total energy. But each of them should have greater than 0.5 and total energy of maybe 3 or 4 or maybe whatever kinetic energy. And then what you do is you sort of open an electronic gate, and this gate will be open only for 100 microseconds, and see if you get 2.2 MeV gamma ray in the next 100 microseconds. If you do, you say, oh, this is likely to be a neutrino interaction. If you don't, gate closes and you wait until the next positron annihilation takes place. So this is the signal that the experimenters identified, and the experiment was led by two people called Cowan and Reines. By the way, there is a sort of an hour-long video on the YouTube by Cowan where he talked about not only this experiment but various aspects of neutrino detection, including this idea I mentioned about setting off an atom bomb to look for neutrinos. So it's worth watching that video. just say, I think in YouTube, if you say Cowan and neutrino detection, I'm sure you will get the video. And they, and also so they have identified their signal, and they have to take data with the reactor on and with the reactor off. And after a year of taking data, the results were not conclusive. They couldn't say with confidence that they have seen a signal for neutrino. But by 1956, with about 3 years of data taking, they could say with confidence that yes, we have seen a signal for detection of the neutrinos being put out by the nuclear reactor. Cowan died somewhat early, and for whatever reason, the Nobel Committee decided to give a Nobel Prize to Reines only in 1995, 40 years after the original experiment. And I had just joined IIT Bombay, and when the Nobel Prize was announced, my colleagues said, okay, you work on neutrinos, so why don't you give a departmental colloquium about the work which led to the Nobel Prize. And I gave the talk. And there was a retired professor called Professor P.P. Carney. He was there in the audience, and then he mentioned one small story. He was a PhD student at University of Rochester around that time. And he says, I remember reading about this observation of neutrino as the headline in the newspaper. And Cowan and Reines apparently saw about 10 events, but their experiment costed $10 million. So whoever was writing the story dubbed neutrino the $1 million particle. But of course, nowadays neutrinos are much cheaper. So that is half the story. Other half, if you remember, I said 2 experiments were launched. So let us discuss the other experiment. Other experiment was led by Ray Davis, who is actually a radiochemist, because separation of radioisotopes became a very important field of study in when it came to building nuclear reactors and nuclear powers. So he started out as a radiochemist, and he developed a technique of we have argon, and argon, if you look up in the periodic table, the atomic number of argon is 18, if I'm not wrong. Helium, neon, argon, 2 plus 8 plus 8. And for lower mass elements, number of protons equal to number of neutrons. So the mass number for argon would be about 36. So this is a isotope of argon, which is somewhat rare, and Ray Davis has developed a technique by which he can extract extremely minute quantities of 37 argon from a large set material. I mean, like roughly one atom out of Avogadro number. I mean, you talk about picking a needle out of haystack. This is much more rarer. And it was felt this technique can be utilized for neutrino detection. So you have a neutrino, it comes and hits a 37 chlorine. Chlorine is the element just before argon with the atomic number 17, and the most common isotope is chlorine 35, but naturally occurring chlorine has about 20 to 25% of 37 chlorine, and this will lead to an electron plus 37 argon, and 37 argon has a reasonably long lifetime, half-life. I don't know exactly, but maybe 2 months or so. So once it is produced, it will stay in your detector for a while, and using Ray Davis's method, you can extract it. So you count the number of 37 argon atoms produced in your detector, and that will be a signature of neutrino interaction. Except Davis saw no signal. In Cohen-Reines, both experiments were done at the same reactor, I believe. Cohen-Reines saw a signal, but Davis did not see a signal. So what does this mean? This gave rise to the idea of lepton number. So you define a number which we call LE. I'm anticipating a little bit, so I'm putting the subscript E, which we define it to be +1 for mu E and electron, and -1 for this antiparticle and positron, and 0 for and you demand that every interaction should conserve LE. Now, so if you look at Cohen-Reines interaction, there is a positron on the right hand side. So final state has Le equal to +1. So initial state should also have Le equal to +1. So you say that the particle which is coming and hitting the proton is an antineutrino. Whereas in the Davis reaction, right hand side contains an electron which has Le equal to +1. So the initial state should have Le equal to +1. So this reaction will occur if it is a neutrino which is coming and hitting the fluorine. But the reactor is putting out antineutrinos, it's not putting out neutrinos. So Cohen-Reines saw a signal and Davis did not. And let us look at the beta decay also. It is N1 plus N1 going to N2 plus E minus plus E bar. Initial Le is 0, final Le has to be 0. There is Le equal to 1 here. So the missing particle must have Le equal to -1. So it has to be antineutrino. So the reactor is putting out antineutrinos, and Cohen-Reines reaction where the final state has Le equal to +1, it could be driven by these antineutrinos. But Davis reaction which has final state Le equal to Cohen-Reines reaction has final state Le equal to -1, that could be driven by antineutrinos. But Davis reaction which has final state Le equal to +1, it could not be driven by the antineutrinos that were being put out by the reactors. Now imagine you are Ray Davis, you developed a very smart technique and you thought you would do great physics. You go to a lot of trouble, you build an experiment, you don't see any signal. So what will you do? Well, you'll get mad, of course. But then you do another experiment. Now you realize where you made the mistake. And you do another experiment to see whether this happens or not. One simple problem. There are a lot of elements which put out antineutrinos, which undergoes the so-called beta minus decay, and the number of elements which undergo beta plus decay, so that if it is E plus and then it will be mu E, the number of such elements is very small and they are quite rare. So Davis had this problem of finding an intense source of electron neutrinos. And here he had the help of a colleague called John Bacall, who pointed out that Sun is producing so many neutrinos, so many electron neutrinos, that every second a billion of them are going through my path. So Bacall did the necessary calculations and Ray Davis designed another experiment and built it. It started running in 1964, and in 1968 Davis released his first result, and based on Bacall's calculation, Davis designed the experiment such that on average he would get 1 argon atom per day. So in a month he and he used to collect argon atoms, I think every 10 days or 20 days. Let's say per month he expected 30 argon atoms. Good news, he got argon atoms. Bad news, he got only 10 rather than 30. So his technique of picking out argon atoms from this 600-ton tank, it actually worked. But What was observed was only 1/3 of what was predicted. That led to what is called solar neutrino problem. So question is there something going on, something wrong at the production? Is the calculation about production of the neutrinos in the sun, is it correct? Nobody has gone and done an experiment in the sun. Sort of educated guesswork. And is Davis's claim of extracting argon atoms, is it as accurate as he claimed? And third possibility, is something happening to the neutrinos as they are coming from sun to earth? So I joined for my PhD in 1982, and for the next 3 years, people used to, both John Bacall and Ray Davis are very highly respected physicists. So everybody would dutifully mention about the solar neutrino problem, but everybody was convinced that you sort of reduce the temperature of the sun by 2-3%, and then the rate of neutrino production will come down by a factor of 3, and that's the solution. But in 1985, two smart Russians proposed a very attractive and very cute solution to solar neutrino problem. And then everybody was convinced that, it is because of neutrino oscillations, and people started working on the solar neutrino problems. Before that, it used to be some problem which you will think about when you have nothing else to do. But after 1985, solar neutrino problem became one of the central problems of research in particle physics. And people worked on it for the next 20 years. And later it was shown that the solution proposed by the Russians was indeed correct. And Bacall's calculations were also correct. Ray Davis's measurement is also correct. And neutrinos are oscillating as they are coming from the sun to earth. Yeah.
So how did they propose that neutrinos are changing their...
We'll come to that later. That's part of the course. So that is the story of electron neutrinos. And in the next class, we will start talking about muon neutrinos. And of course, we need to know about muon neutrinos before we talk about neutrino oscillations. So, even before the story of the electron neutrinos being settled, people started asking awkward questions, and a closer study of those awkward questions led to the proposal that there are actually two neutrinos, not just one, two completely different neutrinos which have nothing whatsoever to do with each other. So in the next class, we will discuss why that proposal was made, and then we will also discuss how that proposal was experimentally verified. Okay. Yeah.
For neutrinos and antineutrinos, lepton is the rejection rate. So why are people still concerned if neutrino is its own antiparticle?
Because the possibility exists.
But lepton number is different. That says that...
No. So that is the thing. Okay, let's talk about something else. For example, we have this law of conservation of charge, and we've had it, I don't know, maybe for 200 years or so. But there are still people who occasionally come up with, you can say, crazier and crazier ideas. to test whether the lepton number, whether electric charge is exactly conserved, or whether it's possible to have a small imbalance in conservation of electric charge. Mind you, quantum electrodynamics forbids the non-conservation of electric charge. Quantum electrodynamics, the exact conservation of electric charge is one of the basic foundations of quantum electrodynamics. If you give up on a conservation of electric charge, quantum electrodynamics completely collapses. So there we have a strong theoretical reason to believe in electric charge conservation, but there are a set of people, and I agree with that point of view, that any conservation law is only as good as the experimental upper limit you have set on it. So let's say one should look it up. I don't know the exact answer. Maybe there are experiments which say that electric charge is conserved to 1 part in 10 power 6. So tomorrow somebody can propose an experiment to push the limit to 10 power 7 or 10 power 8. But here, as far as we know, the lepton number conservation is exact. But as far as the present experimental data is concerned, lepton number conservation is exact. But there is no compelling reason to believe in lepton number conservation. In the case of charge conservation, it provides the basic structure for QED. It provides the very basis for QED, but we don't have any such compelling reason here. So we consider possible violation of it. That is one reason. And in fact, a more important reason is neutrino mass. If it is we believe it is non-zero because we see neutrino oscillations. But the mass is 1,000,000 times smaller than electron mass. We don't know whether it is 1 million or 10 million or 100 million, but it's at least 1,000,000 times smaller than electron mass. And there is something called seesaw model, where if you have Majorana mass, which does not conserve lepton number, then you can have this factor of million suppression without fine-tuning things. So, and that's a very attractive idea, and a lot of people are, 99% convinced that it is correct. So, in that sense, there is actually a compelling theoretical reason to believe that lepton number is not exactly conserved. So that is why a lot of research work is being done on Majorana mass of neutrinos.
Sir, and how do we know? They both are particle and antiparticle appearance?
Actually, this is a very ticklish. The concept of Majorana neutrino is a very ticklish topic, and I certainly don't want to get into it now. Saying that a Majorana neutrino is its own antiparticle, I feel is a lazy way of describing a Majorana neutrino. So there are a lot of technical details, and one has to understand all those details before you try to translate them into ordinary language. the fact that Cohen-Reiner saw a signal, Davis didn't see a signal. That tells you that neutrinos and antineutrinos are different. So then saying Majorana neutrino means neutrino is its own antiparticle, it's going against the experiment. So, I mean, yes, if you look at it in some vague, transformed way, yes, you can think of Majorana neutrino as its own antiparticle, yes. But I would prefer a theoretical description which I can apply directly to experiment. And in that sense, I prefer to think of neutrinos and antineutrinos as separate things.